Okay, so in the last video we talked about the basics of magnetism, and we talked about the properties of the magnetic force, um, as well as right-hand rule number one, which, remember, right-hand rule number one, the purpose of that is to give you the direction of the magnetic force acting on a moving charge, which is moving in the presence of a magnetic field. The other two right-hand rules that we'll talk about later on have nothing to do with force, and so any situation involving magnetic force, that has to do with right-hand rule number one. Okay, so first in this video we're going to talk about something we've not talked about yet, and that is the concept of electric current. And current is going to be a major focus in the circuits unit, which we will do next semester. But for now, we will just briefly talk about the definition of current. Okay, so as we've seen before, charge can be made to move through the presence of an electrical field. We talked about that in 5.1. And so electric field gives you some mechanism to make charge move. Specifically, it's the concept of potential difference, and again, we'll talk about that when we talk about circuits. But you can induce a potential difference let's say in a conductor, and that potential difference will create an electric field, and that electric field will make charge move. And if you want like a simple example of that, if you hook a battery to a piece of wire, a battery is basically a source of potential difference. Okay, so just to give you a really simple example. Anyway, so we understand electric field can make charge move. How quickly charge moves past a point in space is what is known as electric current. Specifically, electric current is defined as the rate at which charge flows past a point in 1 unit of time. And I believe the data booklet defines the equation for current something like this: I equals delta Q over delta T. Okay, and so a capital I is the symbol for current. I don't know why it's an I, but capital I is the symbol for electric current, and again, we'll see that a lot in circuits. Q is, of course, charge, and T is time. And so if you imagine, sitting in like a wire made of copper or something, and you just count how many coulomb flow past you every 1 second, and you divide that many coulomb by 1 second, that number is the electric current. Okay, so that is how electric current is defined, is how much charge is flowing past a point per unit time. The unit for current is the ampere, which interestingly enough is one of the 7 SI base units. And so that's a unit you should be familiar with. And so 1 ampere is basically the amount of charge produced when 1 coulomb flows past a point in 1 second. Okay, so keeping that in mind, when we talk about current, by definition, we are talking about moving charge. And just to give you a really simple example with this calculation, let's say we have a current of 12 ampere. The unit for current, by the way, is ampere. That is a capital A because it's named after a guy whose name was Ampere. And so let's say we're told a current of 12 ampere flows through a wire in 1 minute. Okay, so in writing down my variables, I would write down I equals 12 ampere, and my time is 1 minute, and of course 1 ampere is 1 coulomb per second, and so I need 1 minute to be in seconds. The first question says calculate the amount of charge that flows past a point in this wire in this time. Okay, so if we're looking for Q, this is just a really basic calculation using the definition of current. Okay, current is the rate at which charge flows past a point per unit time. And so here, the amount of charge would just be 12 amperes, that is 12 coulomb per second, times 60 seconds. And of course, it's a really basic calculation. That would just be 720 coulomb. Now, another question we could ask, and again, we'll talk more about this in the circuits unit, but typically, when we talk about current, what we normally mean in most situations is we're talking about moving electrons. Okay, so let's say we have a question, calculate the number of electrons that flow past this point during this time. This is also a question we've done before, because of course we know the charge for 1 electron, the charge of 1 electron, is negative 1.6 times 10 to the negative 19 coulomb. Okay, so how many electrons does it take to make 720 coulomb? That's just a matter of division. if we know each charge represents, a magnitude of 1.6 times 10 to the negative 19 coulombs. Somebody's going to ask me, what about the negative sign? Well, it doesn't matter. For the sake of calculating the number of electrons, it doesn't make a difference. You obviously can't have a negative number of electrons. Okay, so the charge of one electron is this, and so that's just a matter of dividing. And if you divide 720 by 1.6 times 10 to the negative 19 coulomb, you get 4.5 times 10 to the 21 electrons. And so that's how many electrons are flowing past a point per minute, which is actually quite a lot of electrons. It's almost a mole of electrons. And 12 amperes isn't even all that much current, all things considered. Well, I shouldn't say that. It's plenty enough to kill you, for sure. But if you think about, like for example, like a lightning strike could be like in the hundreds or thousands of amperes. 12 amperes is nothing. All right, so now that we know what current is, let's go back to magnetism. Pause it here if you need to write this down. Okay, so of course in the last video we talked about how if you have a moving charge in a magnetic field, it will experience a magnetic force, and the direction of that magnetic force will be given by right-hand rule number 1. Now, since we just talked about current, you might be wondering, what does that have to do with, right-hand rule number 1? Well, if you have a wire that has current in it, that's basically just a bunch of moving charge. And so the right-hand rule number 1, which works for a single charge, obviously would have to work for like a whole bunch of charge. Okay, and so whether you have one single positive charge moving up or a current moving up through a wire, either way, you still have moving charge. And so the right-hand rule we talked about in the last video would still work for that. I'm going to link a couple of videos in here for you to check out, just having to do with magnetic force on a current carrying wire. I say this all just to say that you sometimes see problems using right-hand rule number 1 with magnetic force. Sometimes you see that for individual charges, and sometimes you see that for current carrying wire. And it's the exact same right-hand rule. Whichever way the current is moving is the direction that the positive charge in the wire is moving. Okay, so like I said, it's the exact same right-hand rule that we talked about in the last video. Okay, just something to watch out for. Moving on in the notes, here are some facts that you should probably know about the magnetic force. Because the magnetic force is always perpendicular to the direction of motion, because that's one of the properties of the magnetic force, it cannot do any work on a charged particle. And the reason for that is, remember that work is force times displacement times cosine theta, at least for a constant force. But the direction of motion for a charged particle is always at a 90-degree angle to the force, and the cosine of 90 is 0. And so one of the interesting properties about the magnetic force is that it's not capable of doing work. Okay, which is to say it's not capable of adding or removing energy from a charged particle. Now, it can change the direction, that's true, but it cannot change the speed because that would involve increasing or decreasing the amount of energy. So just an example of this would be if you know what a particle accelerator is, typically particle accelerators use a combination of electric fields and magnetic fields. They use the electric fields to speed up the charged particles, because the magnetic field can't do that because, of what we're talking about now. And then they use magnetic field to make the charged particles move in a really big circle and speed it up that way, and then they can, collide particles together. Okay, so magnetic fields cannot be used to add or remove energy from an object. They can't do any work on a charged particle, but they can be used to force charged particles to move in circular motion. And so, for example, let's say, let me just give you an idea of how this works. So let's say we introduce a positive charged particle into a magnetic field, and let's say, just for the sake of argument, let's say the situation starts right down here at point O. Okay, so let's say we have the positive charge going into a magnetic field. It's obviously moving to the right. Okay, based off of these x's, we know that the magnetic field in this situation is directed into the page. And if you use right-hand rule number 1 to find the direction of the force, okay, then your thumb should be pointing up, which is consistent with this little blue arrow representing the force. Now, what's going to happen is a split second later, the particle is going to be moving in a different direction, because if it has a velocity to the right and it's accelerating up, that means this velocity is going to change because there's going to be an acceleration. And so it's going to change positions, and so a split second later, this positive charge is going to be over here. And now it has a new velocity. And now if you were to apply right-hand rule number 1 again, you would find that the force has actually changed directions, and it's now pointing this way, represented by this blue arrow. And the same thing keeps happening, and the force always ends up perpendicular to the velocity, and so basically what we have is circular motion. Okay, and in this case, the circular motion, we know that in order for an object to move in circular motion, we learned about this last year, there has to be a centripetal force providing that inward pull for the object. And so in this situation, the centripetal force would be provided by the magnetic force. Okay, and so just to give you a simple calculation of that, let's do a basic example with this. Okay, so this problem says a proton enters a region with a magnetic field of strength 3 Tesla into the board, okay, or into the page. Let's say into the page. The proton has a velocity of 4.5 times 10 to the 5 meters per second and is moving to the right, perpendicular to the magnetic field. So just to draw this, the velocity would be to the right, and the field would be into the page. So I'm going to draw X's to represent into the page. Okay, the magnetic force causes the proton to end up in circular orbit. Determine the initial direction of the magnetic force on the proton. Now it says initial because a split second later, like I talked about on the last slide, that direction is going to change. Right when this happens, if you apply right-hand rule number 1, if you have your pointer finger going to the right, remember you have to keep that straight. Your middle finger should be pointed into the page. In that case, your thumb, if you do this correctly, should be pointing up. And so the initial direction of the magnetic force on the proton is going to be up. Now, we're asked to calculate the radius of the orbiting proton. And in this situation, we are assuming that the centripetal force, which remember, centripetal force is the net force acting on an object moving in circular motion. That's equal to mv squared over r. That's made up of the sum of the radial forces acting on an object. In this case, there's only one force on the proton, and that is the magnetic force. Okay, and so here we have the magnetic force, Fb, providing the centripetal force. If I plug in the equation for Fb, we have qvb sine theta equals mvb over r. Okay, because the proton initially has a velocity perpendicular to the field, that means theta is initially 90 degrees. Sine 90 is 1, so we don't even need to worry about that. Also notice there's a v on the left and a v squared on the right, and so one of those v's is going to go away. And so what we end up with is an equation for the radius. If we rearrange this and solve for r by itself, we get m divided by q b. Okay, sorry, let me correct that. mv divided by qb. And so we can calculate the radius of the orbiting proton just by plugging in the mass of a proton, which is given in the data booklet. I think it's 1.67 times 10 to the negative 27 times v, which is given in the problem as 4.5 times 10 to the 5. We know that the charge of the proton, that's 1.6 times 10 to the negative 19. And we know b is 3 Tesla. And so if you plug all of that in to the calculator correctly, you should get 0.0016 meters. And just for simplicity, I will convert that to millimeters. That's 1.6 millimeters. Now, the reason this is interesting is because we can actually if you were actually doing this calculation in real life, you would be measuring the radius because that's something you can physically measure. If you have like a tiny little magnetic field in like a chamber of charged particles, you can measure the radius of that circle. Remember when we talked about the cloud chamber at the very beginning of the year and about how antiparticles were discovered in that cloud chamber? Like that's how the positron was discovered. The way they discovered that type of thing was by measuring the radius of the circular tracks. They put their cloud chamber in a magnetic field, and they saw that some tracks bent one way and some tracks bent the other way. By measuring the radius, you can figure out the mass to charge ratio, and they figured out that based off of the radius, if you have two radii of the same magnitude and one going to the left and one going to the right, obviously those two particles must be the same, but one must be positive and one must be negative, because with the right-hand rule, works exactly opposite for a negatively charged particle, and so that's how the positron was discovered experimentally, okay, using magnetic fields. So anyway, pause there, make sure you understand that concept. Okay, and this is just to give you an idea how if you shoot charged particles into a magnetic field, based off of the amount of deflection, you can infer just some different things about those charged particles. Okay, historically speaking, magnetic fields were also used to figure out information about the different types of radiation. Remember last year in IB Physics 1 when we talked about alpha, beta, and gamma radiation? Okay, well, the way we figured out that alpha particles have a positive 2 charge and beta particles have a negative 1 charge, part of that was based off of which way they're deflected in a magnetic field. And so if you pass all three types of radiation through a magnetic field, you can see three different outcomes. Okay, gamma is not a charged particle, that's just a high energy photon, and so those particles are undeflected. The negatively charged electrons bend up in this situation with a magnetic field coming out of the page, and the alpha particles bend down, but they don't bend down as much. In fact, they have a much bigger radius of curvature, indicating that those particles have a much higher mass. And so that is one way that we were able to ascertain the identity of those charged particles. Okay, but if nothing else, we had an idea of the sign of their charge based off of which way they bent in a magnetic field. Okay, so and that's a useful concept to keep in mind. Okay, so we already know the effect of a magnetic field on a moving charge. I said before, if you have a current-carrying wire placed in a magnetic field, that wire also feels a force because, it doesn't matter if you have a single charge or if you have a current in a wire, that still is moving charge in a magnetic field. Okay, so for example, in this situation, let's say you take a wire and let's say you run the electric current up the wire, like literally up. These green arrows here indicate the magnetic field in this case is going out of the page. And so if you apply right-hand rule number 1, if you put your pointer finger going up and then you rotate your wrist so that your middle finger is coming out towards you out of the page, then your thumb of your right hand should point to the right. And that means if you put a current-carrying wire in a magnetic field, it should be deflected to the right. And it is. And you can do this experiment for yourself, or you can look it up on YouTube. It's a pretty simple demonstration. As long as you have a strong enough magnet and enough current to actually have enough moving charge to be deflected, you can show this experiment. Okay, now there is a slightly different equation that allows you to calculate the magnitude of the magnetic force acting on a length of wire L and carrying a current I in a magnetic field. This equation right here should look very familiar to you because it is very familiar. F equals BIL. B is the magnetic field, I is the current, L is the length of the wire, and sine theta, theta is the angle between I and B. This is basically, this equation is the exact same as the QVB sine theta equation. Okay, one applies for individual charge, QB equals, or FB equals QVB sine theta, and then this one, FB equals, I don't know why the IB writes in this way. I don't really like writing it this way. I always learned it ILB sine theta so that it looks more like this one. These are basically the same thing. One is for an individual charge, one is for a current carrying wire. They both follow the same right-hand rule. Okay, so mathematically speaking, calculations with neither of these equations should be difficult. Really, the only trick is using the right-hand rule number 1 to find the direction of the force. Okay, so we're not going to do a ton of examples with that because calculation-wise, using this equation to do calculations is very simple. Okay, the trick is in the right-hand rule. Pause there, make sure you add that to your notes. Okay, so just to give you an example, this is a common type of IB question. It says a piece of aluminum foil is held between the two poles of a strong magnet as shown. When a current passes through the foil in the direction shown, which way will the foil be deflected? Okay, so pause it here, see if you can figure that out on your own. Okay, now the trick to this question is understanding, of course, that the magnetic field lines in the magnet run from the north pole to the south pole. So here the magnetic field lines are going like this. Okay, so the current in the wire is going this way, and it's kind of hard to twist your hand like that, but if you do your best and you use your imagination, you can kind of see that the magnetic force on this wire is actually going to be directed straight up. Okay, something like this. And so the answer to the question would be B. Okay, this is easily the kind of question you see show up on IB exams on the multiple choice section. Okay, pause there and make sure you understand that question. Okay, so we've already talked about this. Normally, if we had more time, we'd talk more about mass spectrometry, which is kind of an interesting application of magnetism that's used in chemistry a lot. Okay, you're welcome to pause it here and read about this if you're so inclined. Not that you couldn't see a question related to mass spectrometry on the IB exam, but it's really like an application concept. And if you understand the concepts we've been talking about so far, then you could easily do one of these types of problems. Usually you don't have crazy calculations in magnetism other than maybe like using the centripetal force equation, stuff like that. So anyway, moving on, that's just an example of a mass spectrometer. Basically, they're used in chemistry to kind of separate out different isotopes and different elements based off of their mass. Essentially, you take a sample, you like ionize the whole sample, and then you pass it through a strong magnetic field, and based off of the speed and the mass of the particles, it kind of separates out the light particles from the heavy particles. Here are just some magnetism videos that I want you to check out. Really interesting applications. Okay, and then I think we're going to go ahead and stop this video here. I will try to finish up this unit in the next video. As always, please let me know if you have any questions, and I'll see you guys in the next video.